Hi, AP Calculus students. Welcome to your last section of Calculus 7.2. Isn't that amazing? We do divide it up into three parts. What we are going to be doing is finding the volume of solids of revolution and cross sections. So in section 7.1, we were able to find the area between two functions. So when you think of that, that was between we were able to find an area, 2 dimensions from lines, which were 1 dimension, right? And this makes sense. We were integrating, right? Because integrating raises a power, which raises a dimension by 1. So what we're going to be doing here is given an area, how we will collect the area, we will accumulate. Again, that's an integration from a dimension of 2 to a dimension of 3. This is super important because we engineer parts and we need to know their volume. And we use calculus to find that. So we're first going to do, this is called the disk method, which I really should have written. We're going to collect disks so that they form a volume, right? And so let's take a look here. I have, what do I have down here? Oh my gosh, look at this. Look at this. If you take a triangle, right, and you rotate it, there we go. Let's do it this way. There we go. Let's say you take your triangle and you rotate it all the way around an x-axis. Notice you would get a volume that is a cone, right? So again, if this were my x-axis, this marker, my y-axis, sorry, and I rotate it around, right, it is going to form a volume that is a cone. What else do I have down here? Let's say I take a rectangle, the area of a rectangle, and I rotate it around a y-axis, right? And I collect, it's accumulating these rectangles. It would end up forming a volume that is a cylinder. Same with if I took the rectangle and rotated it around the x-axis, it would form a cylinder. I have, let's say that our cross sections are semicircles, right? If we rotated all the way around the y-axis, right, we would have a sphere, a volume of a sphere. This is kind of cool. What if you had a function? This is kind of like a sine function, this shape here, along with a linear function. And what if we rotate it around the y-axis? Look at that. We really do get a volume that is it looks better before. There we go. That is a bell shape, right? And we make parts that are solid that are bell shaped. And so we will be finding volumes of solids of revolution. Okay, which means that we will be collecting areas that are circles or cylinders. I'll show you what I mean. And then so we need to integrate those areas to get those volumes. So today we are doing the disk method, meaning that when we take our area and we rotate around the x or the y axis, we will have a solid that has no concavities in it. 7.2b is obviously we form volumes that do have concavities. That will be called the washer method. All we'll be doing is taking the entire volume that we got from rotation and removing the concavity. So you'll find that we have an integration minus an integration to get the volume that is left. And of course, we can always collect areas, different shapes across an X or Y axis rather than by rotation. And so that will form different volumes. That is 7.2C. So let's go on to what you have in your hand is your notes from 7.2A. Let's find solids of revolution using the disk method. And so here's the notes in your hand, and I will be saying each of the steps as we go, okay? So I have example 1 and example 10, and then my own example, of course, at the bottom of the notes. So we'll be doing 3. This will take a little bit. So let's go through the steps. So on number 1 in your book, they did actually draw the region. y equals a negative x plus 1. Of course, we could have done that very well ourselves. We could have drawn that region. And they would like to rotate this region around the x-axis. And so in your notes, it says, first of all, draw the area and shade is A. That was already done for us. Show the axis of revolution. We did, right? Now, what I do then is I just rotate the area over the axis 180 degrees just to show the front face of the solid, right? I do not shade it in. I always like to know what my original region was, and I'll show you what I mean just for consistency. So there we go. All I did was flip my region. I think I actually did better before, 180 degrees so I could see the front view of my object, right? And so there we go. There we go. So it would appear that I'm going to have a cone. The next thing I show is, so this point I reflected 180 degrees, but it's actually rotating a full revolution around the x-axis. So I like to show that base. This point rotated behind, right, and then in front of the x-axis. So what I have is a cone, which I actually could. I have a formula for the volume of a cone. And so we'll be able to get that volume through integration and compare it because we actually have formulas. Here, I don't have a geometric formula for this shape, which is why calculus is so important. Okay, so now what I'm going to do is parallel, right? I showed my rotation. Here's a circle right here. So parallel to my circular base, but inside of the volume, I make a parallel circular cylinder parallel to the base, okay? These are the cylinders, we'll call them, that I am collecting, that I'm going to integrate. The next thing I do is I show very, very clearly the radius because I'm going to need that of this circle, right? So I use 2 points. And here is the radius, right, of this purple cylinder that you see, okay? Next on our list, I usually just do it so fast I don't use a list. Let's see, parallel to the base. Oh, then we say, we draw the radius and we did. The next thing we're gonna do is write the integral. And here's what I see. It tells you in your notes that if your cylinder is perpendicular to the x-axis, that this will be a dx integration. And if it is perpendicular to the y-axis, like you'll see here, then you will have a dy integration. But I just want you to know why, that this, you can memorize that, but it makes it, watch why this makes sense. Here's what's going on. Okay, I am integrating, I am collecting these circular discs. Notice where x is 0, they are very, very large discs. And as I go to the right and collect these cylinders, when I stop at 1, notice that those cylinders are very, very small, right? And so here's what I'm collecting. Every time when you are doing the disc method, it's pi r squared because it's the area of a circle. But here's where I make my clarification. Why do I keep saying cylinder? Because of the dx here. Here is the area of a circle and dx is a thickness x, right? So, right, this cylinder, right, actually has a little thickness. So it's not just a circle, an area, it's an actual volume, right? I have 2 dimensions, an area times a height here, our dx, and so I'm collecting volumes. And we know integration does that for us. The other reason why, when I have a cylinder, now I'll always use cylinder, perpendicular to the x-axis, I am collecting these cylinders across the x-axis from 0 to 1, right? So here again shows the dx. I'm making a change in x across the axis. So All I need now is don't forget your pi. When students forget their pi on a multiple choice question, they'll always have an answer there where a student forgot their pi. So what goes in here then is the radius, the length of the radius in terms of x. So let's come on down here. We have pi. My x's, my lowest x is a 0, that I'm collecting these cylinders, and my highest x is a 1. My radius would be the distance from this function to this. Now, luckily, this function is 0. So it's a negative x plus 1 minus 0 is the length. Negative x plus 1, don't forget your squared, is the length of my radius. Negative x plus 1 minus 0 dx. Okay, the next thing I'm going to do is actually square. Right? So a negative x times a negative x is an x squared. I have minus x is minus 2x and a plus 1. Let's go a little to the right here. Oh, and I forgot my dx. Let's actually integrate. So I have pi. This would be x from 0 to 1. X squared would be x cubed over 3 minus, right? This exponent would be 2 divided by 2 minus x squared plus x would be the integration. And I will evaluate that from 0 to 1. And I will still not forget my pi. So here's my pi. My f of b is 1/3 minus 1 plus 1. And my volume is simply pi over 3. Okay, notice, let's find the volume for, the formula for a volume of a cone. That is 1/3 pi r squared h. Right, and so that's 1/3 pi, right? Now I can see for my cone, right, it's turned on its side, but the radius is 1, right? And my height is also 1. And notice I still get 1/3 pi. So let's just recap this. I drew my region, I shaded it in, right? I put where the axis I was rotating over. I rotate 180 degrees so I can see the one dimension of my volume. I show a full rotation of a point so I can get some depth, and I make a cylinder parallel to that circular base, and I show the radius very clearly. I write pi r squared because I'm collecting cylinders, right? I have a dx if I'm perpendicular to the x-axis because the thickness of the cylinder really is x, and because my change is x, I'm collecting these cylinders across the x-axis. I find the radius, the length of the radius here was a negative x plus 1 minus 0. I was careful to square it, and then I just did my math. Okay, I'm going to erase, give myself some room for number 10 here. All right, so we can have volumes in terms of y, of course. So in your book, they actually gave us this shape. This is the shape x equals negative y squared plus 4y. And they want this rotated around the y-axis. So notice the first thing I did was draw my region, okay? The next thing, what's the next step? Oh, we show the rotation. The next thing I do is actually show, I flip this region 180 degrees. So I kind of got this almost shower cap or mushroom cap shape, right? Volume that I am trying to find here. Okay, so I'm going to show though, there was actually a full rotation, this point here, like rotated this point rotated all the way around the y-axis so that I can see some depth. The next thing I do then is draw a cylinder that is parallel to that base. All the way across, I am collecting these cylinders. Here is the radius, the length of the radius here. So notice that I am collecting these cylinders right up the y-axis. So let's go ahead and let's write our integration. We have pi. We are integrating a radius squared in terms of y, again, because these are cylinders and they have a little height, they have a little thickness of dy, and my change is up the y-axis I'm going from a lower y to an upper, which, by the way, is a lower y of 1 and an upper y of 4. Now let's write this radius, and let's not forget to square it. Okay, you know what? Let me leave this here so you can see it in the video. There we go, from 1 to 4. So the radius, the length of this radius is actually right minus left, right? So it has to be in terms of y, a negative y squared plus 4y minus 0, negative y squared plus 4y. Don't forget to square that. Okay, let's start some serious math here. Let's first square. So this would be y to the 4th. This will be minus 4y cubed, minus another 4y cubed, right? So that's minus an 8y cubed and plus 16y squared. Okay, and that's dy. Okay, let's take a look, just making sure, minus 4y cubed, minus 8 of those, and then plus 16. Okay, so now I'm going to go ahead and integrate. So this will be y to the 5th over 5 minus, I'm going to raise the exponent 1 and divide by the new exponent. This is going to be a minus 2y to the 4th plus add 1 to the exponent, divide by the new exponent, 16/3 y cubed. And I'm going to evaluate this from 1 to 4. All right, so we have a lot going on here. Let me just check my number 10. Sorry about this. It's late at night, so I'm just kind of. Can I have it right there? Let's see. There it is. All right, so I'm going to do my f of b minus f of a. So just in the interest of time, I'm going to come on up over here. I'm not going to forget my pi. Here's my pi. I'm going to use a bracket to show f of b then minus f of a, because pi is multiplying everything. When I put in a 4, that is 4/5, 4 to the 5th over 5 minus 2, and that's 4 to the 4th plus 16, 4 cubed over 3. That's my f of b. Let me make sure I substituted in right. There we go. 16, right, plus, and 16 times 4 cubed. Okay, minus, and my f of a would be 1/5 minus 2 plus 16/3. Okay, big bracket on that. Okay, now this is getting pretty complicated, but without a doubt, without a calculator. So I wanted to pick this problem because the shape was so easy to see, right? But the calculations do take a bit if you don't have a calculator. So if you mind, I'm just going to make sure that I wrote this right, and I did. And when you do these calculations, you would get 153 over 5 pi. So sorry to cheat you out of the time of doing the calculations, but obviously we can do these. They wouldn't make them so complicated on a non-calculator portion of the AP exam. This would be on a calculator portion because they don't want you to have to spend that much time doing tedious work instead of calculus. Okay, so let's erase and let's do the example that's at the bottom of your paper. Okay, because we have to practice drawing our own region, right? So this is the example at the bottom. Let's say you are given the region between y equals x squared, y equals 4, x equals 0, and x equals 2. And what happens, this region is going to be rotated around the y equals 4 line. What if your axis of rotation is not the x or y axis? This means we have to take the y equals 4 into consideration here. So let's first start drawing our region. Here we go. And let's see, we're going to be over the y equals 4 line. So that's going to be kind of up here. So I'll come on down here. Okay, so my x's are between 0 and 2. So 0, 1, and 2, right? And so notice then when I draw y equals x squared, 1, 2, 3, 4, right? It will go up to y equals 4, right? So let's draw that. Here's 0, 0, 1, 1, 2, 4. Okay, so here's y equals x squared. Took care of that. And it's the region between y equals x squared and y equals 4, which is this horizontal line here between an x of 0 and 2. So here is our region. We will be rotating this region around the y equals 4 line. So let's show that rotation. I'm going to remind myself this is y equals 4, and there's my rotation. The next thing I'm going to do is just rotate this region 180 degrees, right? I don't shade it in. I'd like to know where my original region is, right? So it's rotated across here. So notice then, let's take this point here though. This point was actually rotated all the way around and back. So what we have is turned on the side is a really nice dome shape volume, right? That we are going to be finding the actual volume of because we don't have a geometric formula for this. I'm going to draw a cylinder cross section parallel to my rotation, my depth that I see. There it is. And I'm going to draw the radius. I always draw my radius in the shaded region. Would I still be okay if I drew it in the non-shaded region? Yes, but I like to show the actual radius from the shaded region. Okay, let's go ahead and write our integration. We are integrating pi r squared. And my cylinders are perpendicular to the x-axis. And not only that, they have a thickness of x, and I'm collecting them across the x-axis, so I have dx. My x's are going from 0 to 2. Now we have to be a little careful with the radius here. The length of the radius is this top point minus this lower point. The length of this radius is 4 minus x squared. Right? That's how long that radius is. And we're not going to forget to square the radius itself. So let's go ahead and square. That would be 16 minus 8x squared plus x to the 4th dx. Let's go ahead and integrate now. Not forget our pi, right? And that would be 16x minus 8x cubed plus x to the 5th over 5. And we are going to evaluate that from 0 to 2. Let's quick check on my work here. I'm going to do my f of b minus my f of a, and I'm not going to forget my pi, though I do see because I have a 0, my f of a will be 0. So let's come on up over here. Here's our pi. When I put a 2 in, I have 32. Minus, when I put a 2 in here, that would be 8 minus 64 thirds. Plus, when I put a 2 in here, that is 32 fifths. Okay, now this is something that they would make you do by hand on the, again, let me point out that my f of a is 0. That's where that is. They would make you do this by hand. So let's see if we can go ahead and pull it off, right? Okay, so I see a common denominator of 15. So I'm going to go ahead and say, let's see, so 15, I'm going to get a common denominator plus 15. Okay, let's see. I'm multiplying here by 3. Hopefully I do, right? I multiplied the numerator denominator by 3. That is 6. That's 96. Here I'm multiplying by 5. That is a 0 carry the 2, 32, right? And I'm multiplying 32 by 15. Okay, well, let's do this. 32 times 10 is obviously 320, plus half of that would be 160. So that would be 0, 8, 480. Okay, so 480 minus 320 would be 160 plus 96 fifteenths. Not going to forget my pi. So when I add this up, if this was 100, this would be 266, and I'm 4 short. Let's see, 100, that would be 260, and I'm 4 short, so 256 over 15. Wow, pi. That was brutal. It is actually, what time? It's 8:20 at night, so I'm pretty tired, but it went well. And that is kind of something they would make you do by hand, so I did. So now you can see why we divide section 7.2 into 3 parts. And just take your time, do each step carefully, draw those regions, draw those volumes, draw your circles, show your radius really well. Talk your way through the process. Always write your pi r squared, right? Do I have a dx or not? Do I have a dy? Don't forget to square. Don't forget to square. After you square, sometimes it feels like you integrated, but you actually didn't. So you have to square, integrate carefully f of b minus f of a. It's a real great thing when it turns out that your expression is easy to do an f of b minus f of a. So just take your time with this. We can do this.